The location and resource input page in SAM is where we tell SAM the location we're concerned with. It consists of 4 main parts. At the top is where we choose our location. SAM comes with all of the Tmy3 climate files by default, and that's what's displayed in this menu. If you know that your solar array will be in a location that has a Tmy3 data file, say Pittsburgh, PA, you can quickly find it by typing Pittsburgh into the filter box at the top. Remember that there are only 200 or so Tmy3 locations. You can add other data to this list in a variety of ways. If you have data files in an acceptable format on your computer, you can click Folder Settings to browse to that file or folder. This would be the process you would follow if you're interested in downloading Tmy3 data files for your location from NREL and using those in your model instead of the default Tmy3 data. Similarly, if you have meteorological data from your own weather station or a similar source, you can make your own Tmy3 file from your data through the Create Tmy3 File option. The Location Lookup option allows you to put an address, a zip code, or a coordinate set in, and SAM will automatically download modeled satellite data from Solar Prospector, another NREL data source. This data is only appropriate for concentrating solar plants, not photovoltaics. For more information on this data source, visit maps.nrel.gov/prospector. Once you've selected your location, we'll be using Pittsburgh for this example. You can see the information for your location in the next box down: time zone, latitude and longitude, and elevation. None of this information is editable. Below that is the annual weather data information, including direct normal radiation in kilowatt-hour per meter squared, global horizontal radiation in kilowatt-hour per meter squared, average dry bulb temperature, and average wind speed for that location. As we said, these are the annual values. When SAM performs its simulation, it will be using the hourly values included in the Tmy3 file, not these annual values. If you're interested in seeing what the typical meteorological year looks like, you can click View Hourly Data to examine it in close-up. The default view here is a line graph showing 8,760 data points, one for each hour in the typical year. The fact that each point is a single hour is why the unit for radiation is watts per meter squared, not watt-hours per meter squared. The default view is of global horizontal radiation. Let's use the Zoom In button to get down to a day or two early in the year. In this view, we see 3 typical days at the beginning of January. At this point, if we want to also see what the beam normal and diffuse horizontal radiation look like, we can either add these to our current graph or in a parallel graph by selecting the appropriate checkbox above. This is a convenient way to differentiate between diffuse and beam radiation, for instance. We can see in January that the weather was fairly cloudy. The highest value here is only about 350 watts per meter squared. As the year progresses, the weather gets a little better, and eventually in April and May, on the brightest days, it's getting to 800 or 900 watts per meter squared. Notice that the scale in this tool adjusts automatically. By June, the radiation is hanging around 1,000 watts per meter squared, and as you might expect, as we move into the fall and winter, the values start dropping to the 400 to 500 watts per meter squared range. There are other charts and graphs available in this tool for examining your chosen data set by the hour, and you should be familiar with that capability. Back to the location and resource input page, there are 3 links at the bottom for additional data: the Tmy3 data, the EPW data, and the satellite-derived weather data. As we discussed, the Tmy3 data is similar to the Tmy2 data, except the Tmy3 data is newer and from more sites, but the data is taken from a smaller time span to the Tmy2 data set. The EPW data is used in building modeling software and for the United States is the same as the Tmy3 data. For locations outside of the US, EPW is the data source of choice. The satellite data links directly to the Solar Prospector tool and delivers data on a 10-kilometer grid. While this data is not suitable for photovoltaic arrays, you can use the Solar Prospector tool to find which Tmy3 dataset is physically closest to the proposed PV array by enabling the NSRDB layer in the Solar Prospector tool.